In this video, we're going to talk about nucleophilic addition and nucleophile elimination reactions. In nucleophilic addition reactions, we have a nucleophile, or Lewis base, reacting with a Lewis acid. What's the difference between this reaction and some of the other reactions we've seen? Notice that in this case, the nucleophile is reacting with a carbon double bonded to something. In this case, X is usually going to be an oxygen. Sometimes it can be a nitrogen as well. Let's follow the electrons. Remember, the nucleophile, or electron-rich species, is going to go straight to that electron-poor carbon right there. And the carbon is electron-poor because it's attached to an electronegative atom over here, a delta minus, that's pulling away electrons. That's going to cause this carbon X pi bond to break and put a lone pair on whatever the X group is. So that blue lone pair becomes a nucleophile carbon bond, and the red pi bond becomes a lone pair on the X group. One key thing here is we have to have something that's basic or nucleophilic reacting, and the double bond that we're reacting has to be carbon double bonded to a non-carbon atom. Let's look at an example. In this case, our nucleophile is water. This blue lone pair on water is going to come in to form the oxygen-carbon bond, shown here in blue. The oxygen-carbon pi bond is going to go up to form that red lone pair on the oxygen. And let's do a quick check. On the left side of our equation, we're neutral. On the right, we have one positive charge and one negative charge. Here's another example. In this case, we have hydroxide as our nucleophile. Blue lone pair forms an oxygen-carbon bond. And instead of a double bond, we have a triple bond. So we're just going to push a set of pi electrons up onto that nitrogen there. So one set of pi electrons becomes a red lone pair. We also have an animation to look at. We have two examples in this animation. Here we're going to look at cyanide, Cn-, and keep in mind there's a lone pair on that nitrogen. The blue electrons here are going to form a carbon-carbon bond in blue. I'm going to add in some more lone pairs here so we can keep track of everything. The carbon-oxygen pi bond becomes a red lone pair on the oxygen. So that's our first nucleophilic addition step, and we're going to ignore that second step for now. Let's do the second one now. I'm adding in the lone pairs. The lone pair on the Cn comes to form a carbon-carbon bond in blue. Then the carbon-oxygen pi electrons come up to form a lone pair on the oxygen. Now that we've gone through the mechanism, let's look at the animation. So here's the first example where we have the aldehyde on the left here and the cyanide. The nitrogen is in blue, and the C end is going to attack the carbon that was double bonded to the oxygen. Let's look at that again. The carbon of the cyanide comes to form a carbon-carbon bond, and the electrons went up to the oxygen. Now let's look at the second one with the ketone. So here's the ketone, and here comes the cyanide forming that bond to that carbon and pushing electrons up to the oxygen. One more time. And now we've formed the carbon-carbon bond and push the electrons up to the oxygen. Now let's look at nucleophile elimination. Nucleophile elimination, or nucleophilic elimination, is the exact opposite of nucleophilic addition. In this case, we're going to take electrons on the electron-rich species. Remember that our X group was an O or a nitrogen, typically. And we're going to push those electrons down to form a pi bond and kick out the leaving group. So let's follow those electrons. The lone pair on the X group, an oxygen or a nitrogen, comes down to form an oxygen-carbon pi bond. And here's the lone pair coming down to form the pi bond. Then the carbon leaving group bond breaks to form a lone pair on the leaving group. Carbon leaving group bond becomes a lone pair. The key difference between this reaction and the E2 reaction is that we're forming not a carbon-carbon bond, but a bond from a carbon to an oxygen or a nitrogen. Let's look at some examples. In our first example here, we have an oxygen with a negative charge, and that oxygen lone pair is going to come down to form an oxygen-carbon pi bond. Blue lone pair becomes the carbon-oxygen pi bond. The carbon-chlorine bond breaks to become a lone pair on the chlorine, and it leaves a Cl-. So the carbon-chlorine bond is breaking, and we get a lone pair on the Cl-. Also, notice that in the nucleophile elimination step, we're kicking out something that is a nucleophile. With the nucleophilic addition step, our nucleophile came in, and in the nucleophile elimination, we're kicking a nucleophile out. Here's another example. Lone pair on the nitrogen comes down to form a nitrogen-carbon pi bond. Lone pair becomes a nitrogen-carbon bond. The carbon-oxygen bond becomes a lone pair on water. Carbon-oxygen bond becomes a lone pair on water. In this case, our leaving group is a nucleophile because it has a lone pair on a water. In the top case, we had a negative charge and a chlorine. Both of these are examples of nucleophilic eliminations. What you want to be able to do for the nucleophilic addition and the nucleophile elimination reactions is, given the arrows and the starting material, draw the products, or given the starting material and the product with no arrows, add in the arrows to show how the electrons are moving.